So if you could introduce yourself, please.
Hi, I'm Russ Klein. I'm a program director with Mentor Graphics Embedded Software Division, and I'm going to show you a little bit about our system analysis tool, System Analyzer. So System Analyzer is an Eclipse plugin, and its primary job is to let you go into your system and look both at the applications and the system level and figure out what's going on with your programs so that you can make things go faster, or you can get things done in less time and therefore drop into a low power mode or a sleep mode to burn less power. What we see here in these top 8 lines are 8 cores. We've run a program on the Freescale P4080, which is an 8-core PowerPC device. And these top 8 lines will show us exactly what the 8 cores were doing from the beginning of the program through the end of the program. We can zoom in and take a look at a low level of detail of exactly what the cores are doing. We can see when they're running user space code. We can see when they're idle, that's this gray area. Here we've got a system call in purple and the traps are yellow and so forth. So we can zoom out and view all of that. What we're running here was a program that was originally a single-threaded, single-core program, and we've gone in and broken it up into 25 individual threads. Each of the threads is completely independent. There's no data dependencies. And when we ran it on this 8-core system, what we found is that it ran about 2.5 times faster than our single-threaded implementation. We didn't get anywhere near 7 or 8 times, which is what we expected, or what we at least wanted to get. And so System Analyzer, we used that to dive in and figure out why were we running significantly slower. The first thing you notice at a high level is that these gray areas are cores which are idle. They're not running the user threads. And we can see that at any point in time we've got 3 or 4 cores working together, and only occasionally do we get 6 or 7 working together. So obviously we've got a poor utilization of cores. This thread right here, this top one, is the main thread, and it launches the 25 independent processes or independent threads which are going to execute the work. And what we see is that the main thread will fire off 4 worker threads, and then we see it go into a CPU wait state. This state means that it's been suspended by the operating system and it's not running anymore, although it is runnable. At the same time, we have idle cores. After a while, it goes back and starts working again, and it fires off 3 more threads. It then gets suspended again, and then we run another 4 threads. And so the issue here, we can actually look in these 8 lines right here, CPU 7 through CPU 0, show us, System Analyzer can show us exactly what process was running on the core, the name of the process, and the process ID. And we can see that indeed, once we've launched 4 of the threads, the main thread gets suspended and doesn't get to run again out until this point, where it gets to fire off a few more threads. So what we discovered is that the poor utilization was due to the main thread being swapped out by the operating system, and at that point it couldn't launch any more threads. The threads are fairly short, so they complete their work before the main thread can get back in there and launch more threads. We went through several rounds of debugging this, but ultimately we were able to get the program to look like this. So we created 8 worker threads. Using fixed affinity, we tied them each to a core and then assigned them specific work within the program. And what we were able to do is get all 8 cores working concurrently with just a little bit of idle time at the end of the program. Now, the main thread does go off into a runnable state but suspended, but it only does it after it's launched all 8 cores, all 8 threads. And as a result, we get very good processor utilization. In addition to being able to look at the activity that's going on all of the cores and looking at the state of all of the processes and threads and tasks that are running on the operating system, we can dive down and look at what's going on within each of those threads. So here we have a Gantt chart that shows which function that we're executing across time. So here we've got a list of the functions for this thread, here we've got a list of the functions for this thread, and the functions for the thread down here. Here we've got 3 threads that are running on the P4080 that are contending for a shared resource. So in order to access that shared resource, there's a pthread mutex, or a lock, which is shared to arbitrate access to that shared resource. And so this function right here, we can see that this thread is waiting for the lock at these 2 time periods, again here and again out here. Here this thread is waiting for the lock, and so forth. So what we can do with our trace calculator is we can actually create a Boolean expression which would be true when this top thread is waiting for that lock and false when it's not. And that's what we've created in this waveform right up here, or this trace right up here. So while it's high, he's waiting for that thread, and when it's low, he's off working on other activity. Then we have a trace measurement tool where we can actually measure the width of these periods where the thread is waiting for that, waiting for the lock. And so here we have a vertical line that represents the time that was spent waiting for that resource. And the vertical axis here is time. And so if we zoom out and look at the sort of full view of this, we can see the total time that was spent waiting for the locks during the run of this program. Here and here, we spent actually quite a long time waiting for that lock, and we can see those fairly easily in this graph. We can also calculate a running total, which would give us the total time that was spent waiting for locks, and we've done that here. And so here again, the vertical axis is time, and we can look across the run of the program and see exactly how much time up until that point was spent waiting for the lock. At the end of this, we can see that we spent about 1.02 seconds waiting for the lock, and that was in a run of a total of 3 seconds. So we're spending about 30% of our time waiting for the lock to get at the shared resource. We can then go in and try and see if we can't optimize that in some way. Let's go ahead and close these. So another way that we can use our calculation capability is to sum things up. So here what we've done here is we've annotated our malloc and free function calls. The green line here shows all our malloc calls that were made by the program. You can zoom in and see the individual calls. So these are the malloc events, and these are the corresponding free events. And what we've done is we've done a running total again of both of these, which creates this curve and this curve. And these represent the total amount of memory allocated and the total amount of memory free. Again, using our calculation capability, we can subtract those two, and it gives us this pink line, which represents the total dynamic allocated memory pool over time. So we can see where it peaks, we can see how high it gets, how low it gets. We can also go to the end of the run, and we can see that indeed it ends up at 0, which means we know that we don't have any memory leaks. This lower blue line is the memory allocation associated with one specific instance within the program. So not only can we look at total memory allocation, but we could dive down into a lower level of detail and actually look at what's going on in a more detailed area of the program. So System Analyzer gives us the ability to measure what's going on the system and do calculations on that data and visualize that data to be able to figure out what's going on with our program and to be able to improve it.